So in this video, we're going to present just an example of the kinds of things that we would like to see for the Project 1 argument presentation that you have on Monday for ModSim. I'm mostly making this video for those folks that are in my studio because I forgot to do this in class this morning, and I thought it might be helpful for you to actually have this information. So we're going to talk about what that presentation looks like. I'm going to show you an example and give you a little bit of advice at the end with regard to the presentation. So the format of this presentation is pretty straightforward. It's going to be one instructor. There'll be one or two ninjas potentially in the room, and then 3 students, and in one case, in each instructor's case, 4 students. We'll be meeting probably in the faculty member's office, and you'll be sitting down with that faculty member for a semi-formal presentation. And you should be bringing with you something like 3 or 4 pieces of paper that you use as visual aids to support you while you're making your presentation. You've got 5 minutes to present, and we really do mean 5 minutes to present, and then we'll ask you questions and give you feedback for about 5 minutes. These are going to be assessed. This is the endpoint of Project 1, and we're going to ask you to assess your peers as well as we'll be assessing you. So you need to bring your laptop to do that assessment. That does not mean you should bring your laptop for your presentation. You should be using pieces of paper to make your presentation. In your presentation, we're really going to be looking at 3 sort of distinct things. One is how good your question is. The second is the strength of your model. And the third, it has to do with how well you interpret the results and what kind of argument you're making. And we're going to be rating this on a 0 to 3 scale. This is very much a absolute scale, which has to do with the sort of idea of where we want you to be at the end of this class. So don't expect to get all 3s on your ratings. It will be very rare indeed that we give someone multiple 3s on one of these presentations. So in your presentation, the kinds of things you ought to be doing are basically boiled down to answering 3 questions. The first question is about what your system is and what the question is that you're trying to address about that system. The second question is what the model is and why that model is a sensible model for the system. And then the third question has to do with what kind of work you're doing with the model or what kind of argument you're making. We want to note here that certainly our hope is that you've gotten to the point of actually doing work with the model so you have a reasonable punchline to come to. But if it is the case that your model is not working, you could be making an argument that basically boils down to our model doesn't work, and the reason that we know that our model doesn't work is because, and you could actually show evidence that supports that argument that your model is not sensible. So keep that in mind. We'd like you to do work, but if the work that you do ultimately boils down to arguing that your model doesn't work, that's a lot better than to come in and try to make something that doesn't work look like it does. So let's do a sort of example of that, and this is an example that we'll actually look at a little later in the class. The example has to do with a physical system that is this skateboard trick that's a sort of pivoting skateboard ramp. So the sort of idea here is that you've got a skateboarder who's approaching this sort of seesaw ramp, and you could imagine that as the rider goes up this ramp, they might, if they had enough velocity, go up and cause the ramp to pivot down, and they might roll off. They might, if they didn't have enough velocity, go partway up and then roll back down. And you could certainly imagine it might be possible to actually go up and sort of pivot back and forth on the ramp, and so potentially stay on the ramp for quite a long time. So given that physical system, the question that we're looking at in this particular case is how the time on the ramp depends on how fast the skateboarder is going as they approach the ramp. To answer that question, we've built a sort of simple model, and I'll have this piece of paper is now showing what that model is. So the model involves taking that skateboarder and ramp and abstracting that down to the skateboarder simply being a point mass that's moving along the ramp, and the ramp as being a rigid body that can rotate about its center. And using the sort of laws of physics, we've taken that abstraction and derived a set of differential equations that describe the time evolution of the ramp. We don't expect you right now to be able to look at these differential equations and understand what they're saying or why they're saying it, but were this later in the class, I could actually talk to you about what these equations are and why those equations make some sense. Having presented that model, now let's actually look at whether that model works. So before I show you the model actually doing work, I want to establish that the model is sensible. And so to do that, I've done 2 things with simulation. So I'm running one simulation in time, and with that simulation, I'm plotting a couple of things. One of the things I'm doing is I'm looking at what the position of the skateboarder is. So here you can see a set of keyframes up at the top, and so what happens here is the skateboarder starts out right at the ramp and is proceeding up the ramp. They proceed a little bit further up the ramp. You can see at this point now the ramp is just beginning to lift off the ground. Now the ramp is starting to rotate. The skateboarder is still proceeding forward. As you can see, this red dot is a little bit further forward than this one. The ramp's further down. You'll note the skateboarder is actually rolled back a little bit at this point from where they were here. And then finally the ramp hits the ground and the skateboarder exits to the right. So physically, this sort of looks similar to what we might expect to happen. The other sort of type of validation that we've used for this is that because this system is one that doesn't have any friction or any drag involved, it's a conservative system, so we expect the total energy to be constant. So here we've plotted what the potential energy of the rider is. It starts out at 0 and it's highest when the rider is highest. What the kinetic energy of the rider is. The rider's going fast here, so it has high kinetic energy. The rider's kinetic energy gets lower as they get further up the ramp and slow down. And then finally, what the kinetic energy is that's embodied in the rotation of the ramp. And you can see here that the ramp's kinetic energy is rising. What's important to note here is that the total energy of the system is constant until at this point when the ramp hits the ground. When the ramp hits the ground, there's an inelastic collision with the ground, so there's an instantaneous change in the energy of the system, but then after that, the energy of the system stays constant as well. So we believe the model makes sense both with regard to its qualitative behavior, it behaves the way we expect it to, and in that the equation should conserve energy, and in that it's a conservative system, and the equations indeed appear to do that in the simulation. So having established that the model seems to work, what we're going to look at now is how long the rider stays on the ramp. So how long until the rider gets over here to the right-hand side, and how that depends on what the initial velocity of the rider is. And that's what this graph is showing us. So here on the y-axis, we're plotting the time on the ramp versus the initial velocity of the rider. And you can see some things happening here when we start with a relatively low velocity of, say, 5.5 meters per second. The rider's not on the ramp very long, and you can also see that I've coded here that the rider is actually rolling off to the left. Interestingly, if I make the velocity a little bit higher, the rider stays on the ramp a little bit longer, but the rider also launches off to the left, which is to say that the ramp has not actually hit the ground when they roll off the ramp to the left. This region here, after we get to this peak, is the point where the rider is rolling back and forth on the ramp and is staying on the ramp for quite a long time. If we increase the velocity further, now the rider is exiting to the right, either by rolling off the ramp smoothly or by actually launching off to the right with the ramp not in the ground. So we've actually answered the question with this graph: how does the time on the ramp depend on what the entry velocity is? And as you can see, at about 6.1 meters per second, that's where you'll hit that point where the rider stays on the ramp for a long time. So that's sort of an example of the kind of thing that you might do for this presentation. Certainly, we don't expect you to do something exactly like this, and we've explicitly chosen a system that has nothing to do with sharks, rays, and scallops to show you an example of what this might look like. Let us end with a few sort of pieces of advice. The first and most important piece of advice is that honesty and being critical about your own work is really, really important here. Do not try to pull the wool over our eyes in your presentation. Be clear about what does work and be clear about what doesn't work. It's okay to say my model doesn't work, but you need to be able to support that assessment with evidence that supports that contention. So please don't pretend that your model does something that it doesn't actually do. We're pretty good at identifying when that happens. The second thing that we want to emphasize is that being informal in a presentation does not mean you're unprepared. Rather, it means that you're coming in and you're sitting down and you're having a discussion about something, but you should really know what you're going to say. You should really have thought through this very carefully, and you should have taken time to make these graphs and pictures to actually really represent the ideas that you want to put together. And finally, as we've said throughout this project, it is an individual project. We very much encourage you to collaborate and to work together and talk about things, but at the end of the day, you should be presenting work that you really understand, that you can fully defend and reproduce. And if you're presenting something you don't understand, that's really not okay. So I hope that's a reasonable overview of what you should expect in this presentation, and I apologize to those of you in my section who did not get to see me do this live in class today. Please drop me an email if you have any questions about this, and thanks for your time.